Good afternoon, everyone. I'm just going to take a few minutes to let everyone join our Zoom room for this evening. And so if you just hold on for a couple of minutes and we'll start our introduction. Thank you. So hello, everyone. Welcome to Café Scientifique from all of us at the Faculty of Science at SFU. If you're one of our Café regulars, thanks for joining us again. And if you're new, thank you for joining us for the first time. It's wonderful to see familiar names and community partners, and even some guests from beyond BC's borders. My name is Suzanne Stockdale, and I'm the Senior Director in the Faculty of Science. I'm stepping in on hosting duties today for our regular colleague, Cynthia Henson. She's our Manager of Outreach and Engagement. Unfortunately, she couldn't be here today, but I want to acknowledge the tremendous amount of work she does with managing all of our K-12 and public outreach programs, as well as our many volunteers. Café Scientifique is a Faculty of Science public seminar series where our faculty presenters share their current scientific research and its impact for our local communities and the larger society. Today, our first Café Sci for this academic year, we're looking forward to continued programming through the fall. We typically host 6 to 8 discussions a year, and they're all virtual. They're recorded, and so you can view them on our website if you missed something or you'd like to share a presentation with a friend or family member. We'd love to hear from you and stay in touch. After the event, you will receive a feedback link in an email, and we'd love if you could respond to that. If you're interested as well, you can join our mailing list and receive updates for our next events. I'd like to start us off in a good way by acknowledging that we are privileged to gather today on the unceded and ancestral lands of the Musqueam, Squamish, Tsleil-Waututh, and Kwikwetlam peoples. We thank them for having cared for and been stewards of these lands and waters since long before our time. We look forward to working with them in partnership as we continue to build and grow our communities together. If you know whose territory you're currently on, I invite you to take a moment to reflect on this. If you don't know whose land you're on, a great resource for more information is the website native-land.ca. There you can familiarize yourself with the Indigenous peoples whose land you live and work on. So just a few house rules. Please type any questions you have into the Q&A box. We'll do our best to get to everyone's questions. And if we don't get to the questions during the presentation, we'll get to them afterwards. We'll send those out. The chat will be turned off for the presentation today. And the live transcript is on for your convenience. Note that this is being recorded, as I said, and it will be shared on our website after the presentation. So I'd like to get into tonight's discussion. So I'm pleased to introduce Gopolang Mohlabeng, an assistant professor in our physics department. His research focuses on exploring dark matter and searching for new physics beyond the standard model of particle physics to understand the fundamental puzzles that the standard model cannot explain. Tonight, Dr. Mohlabeng's talk is about dark matter and dark energy. What do we know about it and what we don't? Dr. Mohlabeng gained an interest in physics while studying Albert Einstein, Ernst Rutherford, and Niels Bohr in high school. He completed his undergraduate degree in South Africa and has graduate degrees in particle physics in the United States. We were very pleased to have Dr. Mohlabeng join SFU in 2023. So we're excited to join you tonight, or to have you join us tonight. Welcome.
Thank you very much.
Great.
Yeah, thank you for the introduction. I'm just going to share my screen. Yes.
Great.
So you can see my screen. Okay. So I'm assuming I can start. All right. seeing thumbs up, so I'm assuming I'm gonna start. Okay. So thank you again for the introduction. I'm glad to be here and give this this talk. So I'm going to be talking about unraveling the mysteries of the dark universe today. And before I start, I would like to talk a little bit about the research that I do. So my specialty is theoretical particle, astroparticle physics and cosmology. Essentially, what I work on is proposing models for new physics beyond the standard model of particle physics. And I will talk about what the standard model of particle physics is. And I also work on searching for dark matter using experiments on Earth, as well as various other cosmic probes or telescopes. And then interpreting their data using theory to understand the fundamental nature of dark matter and the dark sector. So going into this talk, the first question I want to ask and I want to bring our attention to is, how big is our universe? And so in order for us to understand how big our universe is, I want to show this this video. So while this video is playing, I want you to pay attention to the length scales here. So we saw a human who is zooming out. So this is California. We're zooming out, keep zooming out. We see now the scale of the Earth. And we keep going bigger and bigger and bigger. Now we're in the solar system. Well, this is the Earth-Moon system. Solar system. Now we see the scale of our galaxy. It's about 100,000 light years across. And we're still zooming out. Now essentially we're at the scale of the entire universe, which is about 10 billion light years across. Now we're zooming back in to the scale of the Earth. So the main point of this video was essentially to show how big our how big our universe is. So we move from scales of kilometers to using light as a distance measure. By looking at like how much distance light moves in a year in order to determine the distance between two different objects in the universe. And another thing you may have noticed is that in our universe, there are billions and billions of stars and galaxies. And we may ask, well, how much of that makes up our universe? So in the other way to ask this is that, is this all that is in our universe? And the answer to this question is no. In fact, all the billions and billions of visible stuff, the galaxies, gas, stars, galaxy clusters, they actually only make up about 5% of the energy density in our universe. And the rest of our universe, we don't know what that stuff is. So we say that the rest of our universe, about 95% of our universe, is dark. Okay, so by saying dark, now this brings us to the dark side. So in order to understand this dark part of our universe, let's go to the dark side a little bit and try to like here with Darth Vader and try to understand what makes up the dark universe. Now, about 27% of our universe is made up of dark matter. All we know about dark matter is that it interacts with us gravitationally, but nothing else. We know that it exists. We don't know what it is. We don't know what characteristics it has. All we know that it's there, and it's the reason that we are here today. The rest of our universe is made up of an even less known entity we simply refer to as dark energy. we have no idea what dark energy is, except the fact that it's the reason that our universe expands at an accelerated rate. So my specialty is working on dark matter and understanding what dark matter is, and this is what I'm going to be talking about today. And so on this cosmic menu for today, what I'm going to be talking about is how do we know that dark matter exists? So I'm going to be talking about what galaxies tell us about dark matter, what galaxy clusters tell us about dark matter, and what the universe after it was born tells us about dark matter. So these are all in the realm of astrophysics, particle astrophysics, and in cosmology. And another thing about this is that all of this evidence that we have of dark matter is actually governed by gravity and nothing else. All we know about dark matter is that it interacts with us gravitationally. And what we're doing, part of my job, is trying to understand if there are any other interactions that dark matter has with us beyond gravity. And we will get to that point towards the end of the talk. Also, I will talk about what we do or don't know about dark matter, what dark matter could be, and what it definitely is not. And also, how do we find dark matter? So once we have some characteristics that we can look for, how do we actually go and look for those characteristics? And this is what I'm going to be talking about towards the end of the talk. Before I delve in deep into dark matter and our galaxies and cosmology, I first want to start close to home. Let's look at our solar system. In order to understand and put everything into context, we first need to understand what gravity tells us about our solar system. And so we know that in our solar system, we have a central object that which is a star that we call the sun. And we have all these planets that rotate around the sun, that actually orbit around the sun. And these planets orbit around the sun because the sun's gravitational field is pulling them towards the sun. But because of the fact that they have velocity, some orbital velocity, they actually stay in their orbits and they don't go crashing into the sun. Now, this can all be explained. The physics around this can all be explained using Newton's laws. And Newton's laws tell us also that planets that are closer to the sun orbit around the sun much faster than planets that are further away from the sun. And now, using this idea and these equations and these laws of physics, we're able to calculate the mass of the sun to be about 1.9 trillion million kilograms. And if we know the masses of the other planets, and we estimate the masses of the other planets on all this other stuff in the solar system, we can measure or calculate the mass of the entire solar system to be about 2 trillion million kilograms. That's about 10 to the 30 kilograms, 10 to the power 30 kilograms. Now, we see this gravitational attraction and we see how it works. But let's for a second imagine that the sun is there, but we don't see it. It's invisible. Meaning that the Earth is always steeped in darkness. So for those of you who have seen the movie called 30 Days of Night, imagine that this is the thing, except we won't have zombies. We're just living normally, we just without any sun. And given those dynamics, that planets are still rotating around this central object that we do not see, we would still be able to measure the mass of the entire, or calculate the mass of the entire solar system to be about 2 times 10 to the 30 kilograms, so 2 trillion million kilograms, and still be able to measure the mass of that central object that we don't see to be about 1.9 kilogram, 1.9 times 10 to the 30 kilograms in mass. And this is the power of Newton's laws. This is the power of gravity, that we are able to measure or to infer something that we cannot see but is there, using velocities of the objects that we do see that are orbiting around that object. And so the early evidence of dark matter was first noticed in 1884 by Lord Kelvin, who estimated that the amount of dark matter by calculating how fast stars were moving around the center of the Milky Way galaxy. And by this, he was able to infer that there must be some missing mass that we cannot see in our telescope. The idea of dark matter, of this using this unobserved matter, was actually first coined by Henry Poincaré when he gave a talk that was based on Lord Kelvin's work. then the stop was in 1906. If we fast forward 30 years later, there's an astronomer by the name of Fritz Zwicky, who basically did the same thing but for larger structures. By looking at the Coma cluster of galaxies, he was able to calculate or measured the velocities of galaxies as they moved around this Coma cluster. And he calculated that there was about 400 times more mass than what he could observe in a telescope in the Coma cluster of galaxies. And this missing mass problem, he called this black material or Dunkelmaterie in German. Naturally, physicists are very skeptical people. No, not many people believed him until about the 1970s, when Vera Rubin, an American astronomer, and collaborators were the first scientists to actually measure the stars, velocities of stars around a galaxy to the highest accuracy using a spectrometer. And this was a new object or a new technology at the time. And what they basically found was that Newton's laws tell us that if I'm looking at a galaxy edge on like this, and I'm looking to, and I go from the center of the galaxy towards the outer edges, Newton's law says, like in our solar system, the closer I am to the center of the galaxy, the faster the stars that are closer to the center of the galaxy rotate. So I'm increasing in velocity. So this is a plot of the velocity as a function of distance from the center of the galaxy. The closer I am to the center of the galaxy, the faster the stars rotate. So this line increases. And as I go outside towards the edge of the galaxy, the stars are orbiting slower and slower and slower, up until when I'm far enough away from the center of the galaxy that if I see a star over here, it's actually it's moving almost at zero speed in relation to the center of that galaxy. What Vera Rubin and the collaborators actually measured was different from what Newton's laws predict. They measured that the closer I am to the center of the galaxy, I do see this increasing motion, or this increasing orbital velocity. But as I go further and further and further away from the center of the galaxy, I actually still see the stars are rotating quite as fast as they were closer to the center of the galaxy. Now, this is really weird, because if I am really far away from the center of the galaxy, how can a star that's over here be rotating almost as fast as the stars that are at the center of the galaxy? And what they inferred was actually there must be something that is causing this rotation, this co-rotation of a star that's over here at the edge compared to a star that's at the near the center. And this is where the idea of dark matter comes in. So they inferred that there must be a halo of dark matter particles that we do not see, or dark matter, whatever, liquid or fluid or whatever, that we just do not see, that is causing this behavior. And they not only measured this in our galaxy, but they measured it in many other galaxies, and they saw the same type of behavior. And they inferred that every galaxy must have a halo around it of dark matter. So essentially what this looks like is that if I go into a telescope and I look at the galaxy face on, what I'm going to see is that the galaxy that I see today that we measure actually rotates almost, the outer edges rotate almost as fast as the center does. But if dark matter did not have, sorry, if a galaxy did not have a dark matter halo around it, essentially this is what it would look like. The center would be rotating much faster than the outer edges of that galaxy. And this is really what we don't see. So what the measurements that Vera Rubin did and her collaborators did, are actually corroborated by simulations and by what we see in our optical telescopes with looking at how galaxies or distant galaxies rotate in relation to the center, to their centers. Now, this was a really big deal. This is a really big deal in terms of the search for dark matter or understanding dark matter. And for all this pioneering work, Vera Rubin, her name will live on for a really long time, because there's a big telescope that is being built currently in South America, which was formerly known as the Large Synoptic Survey Telescope, and is now going to be called the Vera Rubin Observatory. Now, I've talked about the rotation curves of galaxies. But let's ask the question, what if Newton's gravity is wrong? Or maybe our interpretation of Newton's gravity is wrong? we think we understand Newton's gravity, and we think that it gives us a certain relation of the velocity in terms of in relation to the center of a galaxy. But what if that's just not correct, and our idea of dark matter is wrong? What if I could just take Newton's law of gravity and just modify it, and I could fit the data perfectly? This is the idea that proponents of a new theory called, well, not really new, but a different theory of explaining galaxy rotation curves called the modification of Newtonian dynamics, or MOND. They basically saying, I don't need dark matter. I can just take Newton's laws of gravity, modify them with some mathematical structure, and then I can fit the data much better than a dark matter theory could, as shown in this plot over here. What I'm going to show you through the rest of this talk is that in order for MOND, or modification of gravity, to work consistently at all scales in our universe, there has to be I can modify Newton's dynamics at the scale of gravities, but I would need to modify gravity at another scale, and then modify gravity at another scale. Whereas dark matter is just one theory. It's just one theory that fits the entire picture without having to modify too many things that seem somewhat ad hoc. And so let's get into that. So we talked about galaxies, and we talked about how dark matter can interact in galaxies. Now we're going to go to bigger structure, where we're looking at groups or clusters of galaxies. And how can we understand gravity in clusters of galaxies? So a really interesting phenomenon that happens in a cluster of galaxies is what we call gravitational lensing. So the idea of gravitational lensing is that I have a very massive object in the foreground here. There's a galaxy at the back, and the light that is given off by this galaxy is that light is gravitationally bent around this foreground gravitating object. So this gravitational field bends this light around the space-time continuum, and I see this gravitational bending of light in my telescope through these rings here, through this distorted image. So as you can see, this is a galaxy whose light was distorted by this foreground gravitating object, even though it's really in the background of that object. And so we call this phenomenon gravitational lensing, and this foreground object, we call it a gravitational lens. In a similar way to if you're looking at your spectacles that you might be wearing, or contact lenses. You know, this is it's a phenomenon in optics called lensing, really. So light is kind of funneled into a particular focus point that you want to look at, for example. Now let's do a thought experiment again. It's similar to what we did at the scales of the solar system. And imagine that I still have this galaxy cluster, this massive object in front of this galaxy. Now it's there, but I don't see it. Let's imagine that it's there, but it's invisible. This light is still gravitationally bent by this foreground gravitating object that I don't see. And so I can infer through gravity that there must be something there that is causing this gravitational bend in this light. And this is how we determine the existence of dark matter at the scales of galaxy clusters, at much larger scales than galaxies. That, and looking at the rotational curves of galaxies around a galaxy cluster, for example. And one of the biggest examples that I can show of this concept is what we call a bullet cluster of galaxies. So here, this is an animation of two galaxy clusters that merged into each other over a period of time. And as you can see, these two galaxy clusters went through each other. The end result is something that looks like this. And it looks like essentially like a bullet that went through a cloth or piece of paper or something like this. And this is why it's called the bullet cluster. What we can see in our telescope is this X-ray gas. So if I look at it through this in an X-ray telescope, what I'm going to see is this red part of this galaxy cluster. I'm not going to see these blue blobs. Essentially, what these blue blobs in the simulation represent are the dark matter halos around these galaxy clusters. But how do I know that these halos are there and they are at the position that they're at? Is through the concept of gravitational lensing. So essentially, all the stars and galaxies that are behind this blue blob are gravitationally lensed by this object, this massive gravitating object that is in front of them. And we actually see this in our telescopes. And so we can tell that there is a dark matter halo around this cluster of galaxies. Now, as I've mentioned before, dark matter fits this picture very well. So I can explain the data very well through this picture of dark matter. Now, if I said that there was no dark matter and I can modify gravity or Newtonian dynamics, I would need to modify Newtonian dynamics at the scale of those internally in the galaxy cluster itself. Plus, I would need to modify Einstein's gravity, because in order to understand gravitational lensing, I need general relativity, not just classical Newtonian dynamics. So I would need to modify two things in order to fit this, and I would have to do it consistently as the way that I did it at the scales of the galaxies, which is not necessarily possible all the time. And so dark matter still works at the scale of galaxy clusters. Modification of the Newtonian dynamics doesn't necessarily work at the scale of galaxy clusters, or at least in a consistent way. Now let's go to even bigger scales and understand, what does an infinite universe tell us about dark matter? Now, by infinite universe, I mean that the Big Bang happened. Whatever the Big Bang is, it happened. And then after a certain amount of time, so the universe went bang, it was born, and then it started expanding and cooling. And as it expanded, it was cooling. And so there were random temperature fluctuations throughout this process. These give rise to clumps. And as the universe is expanding and cooling, so now because the universe was so hot and in the form of a dense plasma, I have electrons, photons, neutrinos, all these particles that are stable just flying around in this hot soup of stuff. As the universe keeps cooling and expanding, the electrons and the protons start finding each other and they start forming neutral hydrogen. Now, if we know anything about photons, is that photons like to interact with anything that has charge, right? So during this entire time, photons were always interacting, coupling to the electrons or to the protons because they have charge. Now, once the electrons and the protons start forming, binding with each other and start forming neutral hydrogen, the photons all of a sudden have no one to interact with. And so these photons, as the universe kept expanding and cooling, these photons just started flying freely by themselves all over the place. And as the universe kept expanding and expanding and expanding, these photons actually now where we are. So now they're zooming around throughout the entire volume of the universe. So if you think about this as a box or a balloon that keeps increasing and increasing, and I have this photon just zooming around, as the balloon keeps getting bigger and bigger and bigger, now this photon is going back and forth. But if this balloon keeps getting cooler and cooler, this photon is no longer moving as fast, and so it kind of stays localized as the universe keeps getting bigger and bigger, and keeps getting colder and colder in essence. And so nowadays in our local universe today, we see these photons that were born early when the universe was born as well. We call these the cosmic microwave background radiation. And I'm going to label this the CMB. Now the CMB, because they were there when the universe was born, essentially evolved with the universe, and they give us a big picture of our universe today. Now, cosmologists measure these photons, and they can turn this data into a mathematical structure of understanding those temperature fluctuations that happened early in the universe. And this is what we call the CMB power spectrum. Now, the cosmic microwave background power spectrum tells us a lot about our universe. For example, this first peak over here tells us about the shape of our universe, and its location tells us actually that our universe is flat. The second peak tells us about the amount of matter in our universe, and the ratio between the second and third peak tells us about the amount of dark matter in our universe. And how do we know this? Is we actually took the data and we fit it to a cosmological model. For instance, imagine these points here are the data. So you don't need to actually imagine this is actually what's happening. So these points here are the data that we measure from cosmological data of the cosmic microwave background from cosmological telescopes, sorry. And I'm going to fit this with two different models. The first model, the solid one, is a modification of gravity. The second one, which is this dashed or dotted line, is a model that includes dark matter. And as you can see, at this point over here, where the third peak tells us about this unseen matter that actually governs gravity in our universe, we can see that dark matter actually fits this much better than the modification of gravity models do. And so we've shown that dark matter can explain everything, gravitational interactions with matter at the scales of galaxies, at the scale of galaxy clusters, and at the scales of the largest structures in our universe, which are the scales of cosmology. And so it is reasonable to believe that dark matter exists. Now, the question is, excuse me, what is dark matter? Now, before I go into dark matter, an interesting experiment that you can do at home is you can actually see and hear these CMB photons at home. If you still have this TV lying somewhere, I know that they're probably extinct by now, and everyone has an OLED or QLED or like a really fancy TV. If you still have any of these TVs and you're tuning through the channels, you would see the static noise. The static noise actually are the CMB photons that are interacting with your antenna. Or if you have a radio and you're going through the between channels, you hear this shh sound. That is actually CMB photons that are interacting with the antenna. Now, this I found really fascinating when I was a student learning all about this, and I went home and I played around with my radio and the TV until my mom told me to stop. She didn't really understand what I was doing. Anyway, so the question is, why does dark matter matter? Why is it important? Why should we care about dark matter? Well, Einstein's gravity tells us that massive objects cause a distortion in the space-time continuum, hence bending it. We saw this with gravitational lensing, right? And if an object gets trapped in another object's gravitational potential, we have orbits forming, like the Earth-Moon system, as an example, or the system between us and the Earth. We are trapped in the gravitational potential world that the Earth has formed. We're just so tiny compared to the Earth that we really are really so close to the Earth that you don't actually see that we are in this gravitational potential world. And so one example that we can do is to understand why dark matter is important, is to do a kind of an experiment. Whereas we take a rubber sheet and we spread it out, and we put a bowling ball at the center of this rubber sheet. Now let's imagine that the bowling ball is dark matter. Then I take some marbles or ping pong balls and I keep throwing them in there. And as I'm throwing them, I'm rotating this rubber sheet, and we keep rotating it. What's going to happen is that all those smaller balls are going to go towards the center where the dark matter, or this bowling ball, has formed a dip in the space-time, or a gravitational potential well in the space-time, and trapped all those marbles in there. Now, as I'm rotating, some sort of structure is forming in there. And if I imagine that bowling ball is invisible, what I've just done there is I've formed a galaxy. So essentially, what this thought experiment does is show us how dark matter is responsible for forming galaxies. Now, for people who actually do galaxy formation and simulations on galaxy formation, it's not that simple, right? I'm oversimplifying this, but essentially, the reason that galaxies form today is because dark matter is there forming the seed of that through trapping matter in the gravitational potential worlds. Okay, so I like to think of dark matter as the cosmic glue that forms life. Without dark matter, we wouldn't actually be here today. And so when we look at the data, so this is actual simulation from actual data from the Sloan Digital Sky Survey. And on the right, we have a simulation from a computer simulation. And what we see here is that the data actually matches with the simulation very well in terms of how dark matter has evolved from the smaller scales from the larger scales to the smaller scales. We see this cosmic web-like and filament-like structure. And lo and behold, the data tells us exactly this. And so it tells us that we really understand how dark matter has evolved, or how dark matter forms in our universe, or has formed our universe as we see it today. So as I said, I think of dark matter as the reason I am so interested in dark matter is that I think about it as a cosmic glue that forms life. So if dark matter did not form, our galaxy would not if dark matter did not form our galaxy, the solar system would not be here, the Earth would not be here, and we definitely would not be here. And this is why I'm so interested in understanding what exactly this dark matter is. Now, an inconvenient truth about dark matter is that if it's a particle, it must be a new particle. And I'll explain why it must be a new particle. This new particle, we don't know what its mass is. We don't know what its spin is. And spin is some intrinsic angular momentum that each particle has. Is it a long-lived particle or does it decay? We know that it has gravitational interactions. But beyond gravity, we don't actually know what that particle, how it interacts with us, if at all. Is it an elementary particle like an electron, or is a bound state of particles like a proton? The proton is a bound state of quarks, and a neutron is a bound state of quarks. And so if a dark matter could also be a bound state of some other elementary particles that we haven't seen yet. Now, why do I talk about a particle? First of all, I'm a particle physicist, so I think of everything as particles. So I always think about things from a bottom-up approach, like things building on top of each other. And this is why we talk about particles. But also the particle nature of dark matter is actually quite very well motivated. But I'm not going to talk about that today. Now let's talk about particles. So to understand this idea of particles, let's look at this little video, where we now, instead of zooming out, we're zooming in. Again, please pay attention to the scales here. Now, instead of going to light years, we're going to micrometers. So now we're in the atom, and from the distance from the orbit to the nucleus is some really big atomic emptiness. And now we've just seen that protons are formed from an up quark and two down quarks, and a neutron is formed from a down quark and two up quarks, or some combination of that. And essentially, this is where we talk about the building blocks of life. So the video essentially should have started with quarks and then build up everything all the way to the edge, to the scales, larger scales in our universe. But I think it started very well because it gave us a human being for reference, where we could zoom out from that, or we could zoom in. And part of the joy of astroparticle physics is using the smallest structures known to us in the universe to explain the biggest structures known to us in the universe. And those smaller structures here are part of what we call the standard model of particle physics. Now, we all know about an electron. We've all studied about electrons from high school, for example. Now, the electrons form part of a class of particles called fermions. These are the matter particles. Quarks are also part of matter particles, but they're different classification of the matter particles from the electrons. Heavier partners of the electrons are the muon, or the tau particle, and they also have lighter particles, which are partners of theirs, which are called neutrinos. The bosons are the force carriers. So for example, the photon carries the electromagnetic force, the Z boson and the W boson carry the weak force, the weak nuclear force, and the gluon carries the strong nuclear force. Now, unfortunately, gravity is not part of the standard model, such that there is no graviton particle that carries the force of gravity. There's another particle called the Higgs boson, which is essentially responsible for giving all these particles mass. Now, this is not strictly speaking true, but for the purpose of this lecture, let's just say that the Higgs boson is responsible for giving these particles their mass. Now, for those of you who study chemistry, I've kind of given this picture as kind of a classification of these particles without really showing you how they interact. Now, particle physicists are we're not interested in just classifying these particles, but we're interested in essentially how are these particles interacting to give us a picture of the universe as we see today. So I'm gonna burn this picture of the standard model, and I'm gonna show you a more interactive picture of the standard model. And essentially, this is here, it shows that the Higgs boson interacts with anything that has mass. It interacts with itself because it itself has mass. It interacts with all these other particles that have mass. It does not interact with the photon because the photon is massless, and this has been experimentally proven. It does not interact with the gluon because, again, the gluon is massless. Another thing that has been experimentally shown, theoretically and experimentally shown. One of the biggest problems or fundamental questions in particle physics and cosmology today is understanding that the Higgs does not interact with neutrinos. Then you think in the context of the Standard Model, neutrinos are massless, but actually in particle physicists found that neutrinos must have mass because they oscillate. And this was actually awarded a Nobel Prize. And one of the awardees of that Nobel Prize is a professor by the name of Art McDonald at Queen's University here in Canada. And so we know that neutrinos must have mass, but one of the outstanding questions today is where does its mass, the mass of neutrinos come from? Because it's not clear whether they come from the Higgs boson. And so these are the building blocks of life. And so we understand that all of the structure that we see, galaxies, galaxy clusters, stars, gas, only form about 5% of our universe. And this 5% is built from the Standard Model. And so if dark matter is a particle, it must be some new particle that exists beyond the Standard Model, because if it was part of the Standard Model, then we would have seen it. Then I would have had put that extra 27% of dark matter here to saying that it is explained by the Standard Model, but it actually doesn't. So we need a new theory beyond the Standard Model of particle physics in order to explain dark matter and essentially dark energy. Now, what could dark matter be? The range of possibilities is huge. Dark matter could range from anything from something that we call a weakly interactive massive particle, a WIMP, which is about a proton in mass to about 10,000 proton masses. It could be an ultralight particle, something which we call an axion, which is fractions of an electron mass. It could form this class of particle called sub-GeV dark matter particles, which is less than about between an electron and a proton in mass. Or it could be the super heavy particle, which is billions of proton masses, or even heavier than that, which are gram scale particles we call primordial black holes. And so our job is to try and find various ways of detecting these particles, both in our experiments on Earth and in using probes, cosmological and astrophysical probes. Now, how do we find these particles? We can find these particles in the sky, at particle colliders, or in underground detectors. And this plot essentially just says that. So if I look at in the sky, I'm looking at dark matter particles annihilating, essentially changing the mass into energy of the Standard Model. And I'm looking for these particles coming from those dark matter annihilation. So essentially the dark matter is canceling itself out. So I have a two-part dark matter particles coming in, annihilating and converting their energy or their mass energy into the energy of the Standard Model particles. And then I can look for this inside a telescope. Or if I flip this plot around, I can look for a scattering process where the dark matter, if I have a nucleus sitting like this, a dark matter particle comes in, scatters, and causes a nuclear recoil. And I can look for this process. Or I can look the other way around, where instead of looking for a dark matter canceling itself out, I can look for Standard Model particles canceling themselves out and converting their mass energy into dark matter energy. And so let's look, for example, in the sky. This is the process that we call indirect detection. So most likely, this process will most likely happen in dark matter dense regions. And the most probable dark matter dense region we have that's closest to us is the center of our galaxy. So at the center of our galaxy, the density of dark matter is so high that the likelihood of two dark matter particles finding each other and annihilating each other is very, very high. And these particles can then annihilate and convert their energy into Standard Model particles. Or dark matter, if it's long-lived enough but not completely stable, it can then decay today into Standard Model particles. And essentially what this looks like is that dark matter can annihilate into, say, really heavy Standard Model particles that then decay into stable particles like electrons, photons, neutrinos. And we can look for these particles at an array of different telescopes. For example, We can look for low energy photons at radio telescopes, like the Square Kilometer Array or the CHIME radio array that is in Canada. We can look for high energy photons using the high energy spectroscopic system or the Cherenkov telescope array, or we can look for neutrinos at an experiment called IceCube, which is in the South Pole, or an experiment that is actually being built currently on the coast of on the Pacific coast of Canada, called the Pacific Ocean Neutrino Experiment. And there's actually a professor at Simon Fraser University who's working on building this. And in fact, there are two professors who are working on building this this big experiment, this big flagship Canadian experiment. The other way that I can look for dark matter is to produce it inside a collider, inside an experiment. And the most probable experiment that I can do this is inside a particle collider or a particle accelerator or an atom smasher or whatever you want to call it. So for example, if I look at, if you pay attention to this red dot here, this is how it works. So I take a bunch of protons and I accelerate them in a ring, an accelerator ring. I take another bunch of protons, I accelerate them, but in the opposite direction. And as these bunches of protons keep accelerating, they get faster and faster and faster and faster. And then I arrange for these protons to meet at a certain point, bunches of protons to meet at a certain point. And in that tunnel, I put a big material there that I call a detector that is going to look for these two particles smashing with each other. And essentially what this looks like is that in the tunnel, as these bunches of protons are coming in together, they smash into each other and they produce stuff. And so they're converting their energy into the energy of other stuff. And part of that stuff that is being produced can be dark matter. Now, dark matter does not really interact much or interacts very feebly with the rest of the standard model particle. The dark matter is just going to fly away. And what I look for is missing energy. I use the conservation of energy. I know the energy that went into the system. I can count the energy that goes out of the system, and I can tell you the missing energy that went away. And so I can then infer the mass or the properties of the dark matter particles that got out of that. And this here is a picture of a detector. This is the ATLAS experiment at CERN as part of the Large Hadron Collider. And for reference, you can see human beings here. So these are people, and this is how big this experiment has to be. This is the tunnel that these bunches of protons are going to be going in through. And so once these protons hit each other, they have to go through all this materials, and they get detected by these different layers in order to determine the properties of all these particles that are coming out of that. And so this is really, really fascinating science. And again, there are a lot of people at SFU who are working particularly on this ATLAS experiment. Another way that I can look at this is not to look at really high energy collisions, but look at low energy fixed target experiments. For example, if I shoot a bunch of electrons or protons at a fixed target, say I put a block of aluminium and I shoot a bunch of electrons there, and essentially I look for what comes out of this interaction. Now, in order to isolate the dark sector particles, I'm going to put this in say, a rock. I'm going to put this target in a rock. And the idea is that this rock filters out all the standard model particles. And essentially all the dark sector particles come out. I put a detector downstream, and the detector, the dark matter or the dark sector particles then go and scatter inside my detector. So if I know I've filtered out all the standard model particles, and I hear a ping, I get a ping on the detector here, then there must have been a dark sector particle that went through this rock and was able to interact with that detector in further downstream from my interaction. So these are some of the ways that we can look for dark matter in our experiments, or produce dark matter in our experiments here on Earth. Now, the last way talks about dark matter scattering, which is a process called direct detection. And the process of direct detection is simply banks on the fact that we are in our galaxy that is rotating, and we're surrounded by a halo of dark matter. Now, let's assume that this halo is spherical. Makes our lives easier to assume that it's spherical. And essentially what's happening is that as we're rotating in this halo, the dark matter is coming at us at the same rate as we're moving around the center of the galaxy. What I mean by this is that the galaxy is rotating at some rate, which is about 220 kilometers per second. So if we're here, we're moving around the center of the galaxy at 220 kilometers per second. Now, if I have a dark matter halo surrounding this galaxy, essentially what I'm seeing is dark matter particles coming at me at 220 kilometers per second. Here. And what I could do with this is to say, well, I don't need to build any collider or bank on these dark matter particles annihilating with each other. All I need to do is just put a detector deep underground. So build a really big detector, put it deep underground, and wait for one of those dark matter particles to come in and interact with the standard model particles inside my detector and cause a recoil, kind of like similar to billiard balls or snooker, for example. Dark matter comes in and hits one of those particles. It causes a nuclear recoil. This nuclear recoil actually releases light, and I put some electronics in that detector, and I can detect this light from this nuclear recoil. And from using momentum and energy conservation equations, I can reconstruct the mass and properties of the dark matter particle that came in. Now, the dark matter particle does its job, hits this nucleus, and then just flies away. It's just coming, the nucleus is in its way. So it's just coming in, hits it, and flies away. And I can do that, in this experiment, I can calculate the properties of the dark matter that way. And so far, this has been these are the searches that have been happening for the past many decades. We haven't seen a signal yet, but our search continues. And essentially, like this dark matter may be hiding in plain sight, and we are currently searching for different ways of looking for this dark matter by looking at new experimental searches and coming up with new theoretical ideas. And that really is part of my job as a particle physicist. And yeah, that's it. Thank you.
Gopi, if you want to stop sharing your screen there, maybe we can just have a
Oh,
few questions.
okay.
So there was a question about, are you a Star Wars fan? It looks like you might be a Star Wars fan.
I am I actually started watching this Disney Star Wars TV shows. I'm not really a big fan of the movies. I actually really like The Mandalorian a lot.
I thought it was fascinating to see the full stretch of particle physics from the atom and from the smallest points of life to the universe. And it was such a wonderful way to appreciate the scale from small to large that we see within our universe. And so I'm just curious, there was one question that came up in looking at calculating dark matter in the Milky Way. Do you roughly need to know where the dark matter is located in order to calculate things about it within the Milky Way or within our galaxy? Or do you assume that it's evenly distributed?
So the dark matter is actually not evenly distributed. So looking at the dynamics of the galaxy and looking at some inference from astrophysics, we have an idea what the density distribution of the dark matter is like. So we know that the dark matter must be more dense in the center, towards the center of the galaxy, than it is towards the outer edges of the galaxy. And this is what we use to calculate some of the properties of the dark matter. For example, when I talk about indirect detection and dark matter particles annihilating, I'm actually using this idea of a galaxy, of a dark matter distribution that is higher towards the center of the galaxy than towards the outer edges.
Okay, thank you. Now, what about when there is a detector, and how do you know that it's interaction with dark matter and not some other particle?
That's a very good question. And part of the reason that we put a big detector deep underground is the fact that standard model particles get filtered by the rock. We call this an overburden. And so there are a lot of particles that are produced by the atmosphere. And these are particles like neutrinos that are produced in the atmosphere. We also have particles called cosmic rays that are come from further away in our galaxy. And they can come into the detector and give us the same type of signal as a dark matter particle. But if we put these deep underground, we can actually filter those particles out. And if a dark matter particle comes in, because it's so weakly interacting or so feebly interacting with, with the standard model, the chances of it interacting in the rock are high, but there is a non-zero probability that the dark matter comes in and interacts inside the detector.
And is that the same for water when you're putting a detector in the ocean?
Yeah, so we don't really talk about dark matter except like certain class of models of dark matter in water or ice. Usually for these non-relativists, because these detectors in ice or water are really specialized detectors, and they're essentially looking for really fast-moving particles like neutrinos. They don't really detect with dark matter the particles that are moving really, really slow, like the dark matter.
Okay.
So the dark matter direct detection experiments are specialized to look for dark matter, which is moving really, really slow compared to neutrinos.
So that's the sort of work that the other physicists at SFU are working on.
Yes.
Okay, that's interesting. And do we know what interacts with dark matter? Do we know what it doesn't interact with? And so how do we, I guess we know how do we know what type of detector to use to detect it?
Um, that's something we don't know. So essentially part of the study of dark matter is doing everything that we can to rule out some things that we don't know. We don't know about the dark matter. So we postulate some theories. So part of my job is coming up with theories of where dark matter, what dark matter could be and what the signal looks like. And saying, can this experiment go and look for it? Can that experiment go and look for it? And if we go to that experiment and search for it and we don't see it, then we learn something about the dark matter. And we say, okay, clearly dark matter cannot interact with this or cannot interact with that. And so then we rule that out and then we go to the next thing and so forth.
So is there any interaction between dark matter and dark holes, like a black
Black hole
holes?
and black holes. So there are these tiny black holes, which we call primordial black holes, which are black holes that are produced early in the universe. They can be dark matter, but if they are dark matter, they cannot be all of the dark matter because they're just too big to form the structures, all of the structure that we have today. But then in terms of the supermassive black holes, like with the one we have at the center of our galaxy, they don't necessarily have, aren't necessarily dark matter. Like, in fact, they're not dark matter.
So that's
This,
interesting. Sorry, go ahead.
no, I was just saying that they're not dark matter because they're very localized, and we need a halo around our galaxy, not this localized thing at the center of it.
Right. Okay. So one thing I was wondering about is when you think about the early universe and the development of galaxies in the original sort of going back to close to the Big Bang, and maybe galaxies that are developing that are newer, is there differences in dark matter with the older and the newer galaxies? Like, do you see there's changes in how it is affiliated with those galaxies?
Because we don't measure dark matter directly, there's no way that we can tell whether dark matter the dark matter has evolved. The one thing that we do see in older versus newer galaxies is the stars. We can tell how stars move in the galaxy. So, for example, if you look at the galaxy evolution, younger galaxies tend to be more spiral, if I'm not mistaken. Maybe some astronomer might be mad at me for saying this, but as far as I remember from taking a course on galaxy formation, younger galaxies tend to be more spiral, more bluer, brighter stars, and older galaxies tend to be more elliptical and have older, redder stars. So as far as I remember, that's the major distinction that we can make with these galaxies. But in terms of the dark matter halo around it, it's not very clear that we can make such a distinction. The only thing that we can say is that an older galaxy would more likely have swallowed the smaller dwarf galaxies around it to form the halo that it has formed today, whereas a younger galaxy may have some subhalos around it that it hasn't swallowed as yet. And interestingly, there is an experiment, not an experiment, but there's a telescope called Gaia that is looking for how big galaxies tend to swallow their smaller counterparts and how the dark matter halos themselves have actually been swallowed to form the halo of the dark matter, the dark matter of the bigger galaxy.
So as the bigger galaxy swallows the smaller galaxy, the same thing's happening with the dark matter.
Yes, it's absorbing the halo. So we call this tidal stripping. So the halo is actually stripped up, and then you see this streak of stars. And so Gaia actually has reported these clumps and streaks of stars, and we believe that the dark matter halo is actually tracing this. And this can actually go into our calculations of direct detection. uh, of dark matter. Yeah. Very interesting.
So do you think you'll ever be able to directly detect dark matter?
Yes, I do believe that.
Yeah, that's
Yeah,
interesting because it's always hard when you can only see the results or the effect of something. You can't directly see what you're trying
yeah,
to observe.
yeah.
So there's another question is, can gravitons be dark matter?
It is possible. We haven't ruled them out. They just really, really weakly, because they carry up gravity, they just really, really, really weakly interacting. So it is possible that they could be dark matter.
Okay. And now, why does the universe cool as it expands, and how do we know it cools?
So this is a concept of the thermodynamics, really. So it's a question of the way I think about it is conservation of energy. So if I have this really tiny blob and I have a set amount of energy inside that blob, or like take a balloon and put, I don't know, hot water in it and blow up the balloon. As this balloon expands, right, the amount of energy remains constant in that. And so, but that same amount of energy is going to be divided into the entire space of that balloon. If I'm in the center of the balloon, I'm going to be feeling less and less heat, or less and less a lower and lower temperature as this balloon is expanding, and that energy keeps getting divided in between that balloon. And so if I think about the universe as this balloon, and the constant amount of energy is this temperature, or there's this division of temperature, division of energy, essentially this is how we know that the galaxy or the universe is cooling as it expands. And we've measured this actually. So the simple answer, we measured it, but I just tried to explain it from a thermodynamic point of view.
Hmm, that's fascinating. Now, on the slide with the blue rubber mat, you said that dark matter is what formed the galaxies, but I thought that the black holes were at the center of the galaxies.
Yeah, so I made it very simplistic. It's a very simplistic analogy, but the dark matter is what is forming the galaxy, because it forms the gravitational potential well that causes all the structure to get trapped and clumped inside, and form this structure that we now call a galaxy. Now, because of this clumping, and I have a lot of material just really compact inside this region, I start having the structure starts gravitationally collapsing onto itself, and this is what forms a black hole. Yeah.
Okay, thank you. So I guess one last question. So again, right now we can observe the standard model particles that result from the decay or annihilation of the dark matter particles. And so I guess my question is, how do you think we're ever going to observe directly the dark matter particles?
Through the process of direct detection, through the scattering.
Okay.
So if the dark matter particle is itself coming in and scattering, and uh, um, causing the scatter of the nucleus or an electron or whatever. And so, but I should say that it's not one or the other, so one method or the other. It's all of them combined. So we call these complementary, because if I see a scattering signal, right, I need to go to a collider in order to verify that this is actually was a dark matter signal. And how I do that is by saying, well, the interaction strength that the dark matter had to scatter with the nucleus is the same interaction strength that a nucleus should have in order to produce a dark matter inside my detector. So if I see the scattering signal, then I have to see the signal at a detector.
That's very complicated, but it's
Yes,
interesting because then you have to work in very large groups
yes,
collaboratively to be able to do this work.
or in tandem. We should
Yeah,
say, like, we
yeah,
work in tandem. So
in
yeah,
tandem. So I have another question here. Could dark matter exist inside the standard model particles?
no,
Okay, they're quite
no, it
separate.
cannot be. So yeah, we thought at some point that neutrinos were dark matter, but neutrinos are moving so fast after the universe is born that they don't have enough time to stop and form these gravitational potential wells so that the regular structure can form galaxies. And so we say if the neutrinos were dark matter, they would wash out all the structure. We wouldn't have structure formation today.
That's excellent. Thank you so much for your talk today. And I know that that people will be very interested in hearing more about what you're researching as you spend more time at SFU, and we're really looking forward to your research. I know I am. I'm very excited. And as the skies get darker and winter comes, people have an opportunity to spend more time at least looking up at the night sky and thinking about what might be out there. For those who are not aware about our Starry Nights events, we have an observatory for visual objects, certainly up here on the Burnaby Mountain campus. So if people are interested, you can check it out on our website. So thank you again, Gopi, for your presentation today. We've really enjoyed that.
Thank you.
Thanks.
Okay.
So thank you again. We've reached our time and finished our time for this evening. If there are questions, I think we answered all the questions, but if there's anything else, please reach out to us by email. And many, many thanks to Dr. Gopi Mohlabeng for sharing his experience and his knowledge. And thank you for joining us. We hope to see you at our next Café Scientifique in October. Have a good night.